All right, let's talk about a little component that is absolutely fundamental to modern electronics, but one that can feel a bit mysterious. We're going to pull back the curtain on the Junction Field Effect Transistor, or JFET. And trust me, by the end of this, you'll see it's really not that complicated. In fact, it works a lot like a simple water faucet. So let's start with a puzzle. How do you control a river of electricity? I mean, you can't just reach in and block it, right? So what if you could control that flow without physically touching it at all? What if you could use something like an invisible force field? Well, that invisible force field is exactly what a JFET does. It's a special kind of transistor that uses an electric field to manage how much current gets through. Now, the key term here is unipolar. All that means is that it only needs one type of charge carrier, usually our good old friend the electron, to get the job done. This is a bit different from other transistors, and it's what makes the JFET so elegant. To make this super clear, let's lock in that analogy we're going to keep coming back to. Just picture a JFET as a high-tech faucet, but instead of controlling water, it's controlling a flow of electrons. It is, quite literally, an electronic valve. Okay, so if we're going to understand how this electronic valve works, we first need to know what it's made of. So let's pop the hood and take a look at the anatomy of a JFET. Every JFET has three main connections, or terminals, and they line up perfectly with our faucet idea. First, you've got the source. That's the inlet pipe where the electrons flow in. Then you have the drain, which is the outlet spout where they flow out. And most importantly, you have the gate. That's the handle on the faucet, the part you use to control everything. So what is this thing actually made of? Well, in a standard JFET, the main pipeline for the electrons is called a channel, and it's made from something called N-type material, which just means it has a lot of free electrons ready to move. Now, this channel is surrounded by the gate, which is made of P-type material. It's kind of the opposite. It's hungry for electrons. And right where these two different materials touch, they form a really important barrier called a p-n junction. All right, we know the parts. Now for the magic. How does turning that handle, the gate, actually control the flow of electrons? Let's get into the mechanics of how this valve actually works. It all comes down to something we call the squeezing effect. Here's how it works. When you apply a negative voltage to the gate, you create that electric field we talked about earlier. This field pushes electrons away from that p-n junction, and it creates a zone where no current can flow, called the depletion region. As you increase that negative voltage, this region expands and literally squeezes the channel, making it narrower. And you guessed it, the narrower the channel gets, the harder it is for electrons to get through. Now, this squeezing action leads to two very important states. The first one is called pinch off. This one's a little tricky. It's like turning the faucet handle to a certain point where the flow is steady and consistent. The channel is squeezed, for sure, but a stable maximum current is flowing for that specific setting. Then there's cutoff. This is much more straightforward. It means you've applied enough negative voltage to the gate to squeeze that channel completely shut. The faucet is turned all the way off, no more current. And this brings up a really key point. It is so easy to think pinch off means the flow stops, but it doesn't. The channel isn't completely closed. Instead, the current just hits its maximum possible speed for that gate setting and stays there. It saturates. Think of it like the valve is now locked in place, letting a perfectly steady stream flow through. So we have this incredibly precise electronic valve. We can gently squeeze the flow of electrons using just a tiny bit of voltage. That's a really neat trick, but so what? Why is that useful? Well, the number one reason is for amplification. This brings us to the JFET's real claim to fame, its electronic superpower. What is the one thing that makes this component so special and so useful in the world of electronics? The answer is this number right here, around 100 million ohms. That's mega ohms. That is the JFET's typical input resistance at its gate. To put that in perspective, it's like having a faucet handle that's so perfectly insulated and frictionless that it takes almost zero effort to turn it. This insanely high resistance is the key to everything. And why is that a superpower? Because it means the JFET can listen to a signal without disturbing it. It draws almost zero current from whatever you plug into it. This is huge. It means you can take a very weak, delicate signal, maybe from a high-quality microphone or a sensitive medical sensor, and the JFET can read it without changing or degrading it. It's the ultimate clean, low-noise way to make a very tiny signal much, much bigger. And that's the whole game right there. You use a tiny, almost effortless change in voltage at the gate to control a much larger flow of current between the source and the drain. And that, my friends, is the definition of amplification. So to wrap this all up, let's put the JFET into context. How does our electronic valve compare to the other big player in the transistor world, the bipolar junction transistor, or BJT? This table really breaks it down. A BJT is current controlled. You have to feed it a little bit of current to control a bigger current. But a JFET, as we've seen, is voltage controlled. The biggest deal, though, is that input resistance. It's low for a BJT and sky high for a JFET. This basically makes the JFET the undisputed champion for amplifying weak signals with very little noise. You could say the BJT is a fantastic, all-around workhorse, while the JFET is more of a delicate surgeon. And the legacy of the JFET is absolutely massive. The core idea of using a field effect to control current didn't stop there. Oh no, it was refined, it was improved, and it led directly to the creation of the MOSFET. And the MOSFET is the tiny microscopic switch that is the fundamental building block of basically every computer chip on the planet. There are billions of them inside the device you're using to watch this right now. So we started with a simple water faucet and ended up with a component that laid the groundwork for our entire digital age. It really makes you wonder, as we keep pushing the limits of technology, shrinking our components down to the size of individual atoms, what on earth will the next electronic valve look like?